Good morning, champs. Now let's solve an Exergy problem with a heat exchanger. A hot air stream transfers heat to a colder water stream. The air enters at 650 Kelvin and 2 bar. It leaves at 450 Kelvin and 1 bar. The air mass flow is 0.8 kilograms per second. The water enters at ambient conditions. So the water inlet temperature is 300 Kelvin and the inlet pressure is 1 bar. The water temperature increases by 15 Kelvin. So the outlet temperature of the water is 315 Kelvin. We assume the heat exchanger is adiabatic toward the environment and there is no shaft work. First, we calculate the heat transferred from the air to the water. For the air, we use the enthalpy change. Since air is treated as an ideal gas, the enthalpy change is heat capacity times temperature difference. So the heat transfer is mass flow times heat capacity times the temperature drop of the air. Using the values, we get about 160.8 kilowatts. This is the heat transferred to the water. Next, we calculate the exergy of the entering air stream. Specific exergy tells us the useful work potential per kilogram. For an ideal gas, the exergy formula contains a temperature contribution, an entropy penalty, and a pressure contribution. At the inlet, the air is much hotter than the environment, and it is also at a higher pressure. So we expect the inlet exergy to be large. Using the ideal gas exergy formula, the inlet specific exergy is about 178.3 kilojoules per kilogram. Since the air mass flow is 0.8 kilograms per second, the inlet exergy rate is about 142.7 kilowatts. Now we calculate the outlet exergy of the air. At the outlet, the air is still hotter than the environment, but its pressure is now equal to ambient pressure, so the pressure contribution disappears. The outlet specific exergy is about 28.5 kilojoules per kilogram. Multiplying by the air mass flow gives an outlet exergy rate of about 22.8 kilowatts. Now compare inlet and outlet. The air exergy decreases from 142.7 kilowatts to 22.8 kilowatts. So the air loses about 119.9 kilowatts of useful work potential. Now we look at the water side. First, we calculate the water mass flow using the heat transfer. The water gains 160.8 kilowatts of heat. Its temperature rises by 15 Kelvin. Using the water heat capacity, the water mass flow becomes about 2.56 kilograms per second. The water enters at ambient conditions, so its inlet exergy is 0. At the outlet, the water is slightly warmer than the environment at 315 Kelvin. Using the incompressible liquid exergy formula, the outlet specific exergy of the water is about 1.52 kilojoules per kilogram. Multiplying by the water mass flow gives an exergy gain of about 3.89 kilowatts. Now we combine both streams. The air loses about 119.9 kilowatts of exergy. The water gains only about 3.89 kilowatts. So the total exergy change is negative. The missing amount is the exergy destroyed inside the heat exchanger. The exergy loss is about 116 kilowatts. This is the most important result. Energy was transferred from the air to the water, but most of the useful work potential was destroyed. Why? Because heat transfer across a finite temperature difference is irreversible, and irreversibility creates entropy. Entropy destroys exergy,